Swayam Prabha. Digital India. Educated India.
And you want it to be one variable.
A variable which dictates the curve.
Exactly. See, the problem is that the curve is, if you take a curve in the plane, you normally write an equation which involves x and y. There are two variables now, okay, but curve should be controlled by only one variable. So what it means that both x and y should further be written in terms of a t, x equal to x of t, y equal to y of t. So the whole curve is controlled by the t. The only proof that it is a curve is that it is controlled by a single variable. Okay, you have to make that parameterization. Then you have to do calculus with respect to this variable t on these two coordinates x, y. If it is a plane curve, if it is a space curve, you will get xt, yt, zt. You will get three scalars functions, and they will all depend on the same t, and you have to do calculus with respect to t. But now you have three functions.
Sir,
you understand?
Parameterization in 3D curves, like they would be much more complicated than that of 2D curves.
Of course.
So how should we go about, like, just how should we go about, like, parameterization?
Okay, so these are all, very vague questions, and then you have to look at lot of pictures on the web.
No, sir, like for parameterization of 2D curves, it's like mostly it's substituting the slope or the substitution of angles for the curves.
No. I think, see, you are asking a very vague question, okay, for which there are very general theorems, and they are not, it takes time to explain, okay. So what we normally do is that we look at standard, curves that we know, algebraic and analytic curves, and then you have general theorems. But the question is kind of too vague, okay, and I don't want to get drawn into this because I am trying to say something else, okay. But I invite you to go to you just go to, for example, Google, and then search for parametric equations of curves, and you will find a hell of a lot of material, okay. You try, in fact there is something called math curve, okay, and then there are encyclopedias of curves which lists out curves. They are mind-boggling encyclopedias are there. Let me see if I can show you, okay. It lists curves, it tells you what is the radius of curvature, what is the polar equation, what is a pedal, what is the evolute, what is the involute, all kinds of crazy things are there. I mean, last century it was very heavily studied over the last few centuries. So it's a very it's a pretty complicated thing, okay. I mean, it can be pretty complicated. There are curves which are quite complicated. Yeah, so I will request that, please, I am very happy with your asking too many doubts, but then I see that if all my time is going to be consumed in that, I cannot say what I wanted to say, okay. So you should kind of allow me also to tell you what I want to tell you, okay. I appreciate your questions, but also give me a chance to finish what I started. I am just, running out of time. So let me say a couple of things, okay, and then we will get back to questions, okay.
So, very briefly, can you explain what is BP again?
What is?
BP again.
So I am saying it's a very, very simple thing. You have this curve. At the given point, you have the so-called tangent. You have a tangent vector, right? So that is this tangent vector, TP. All right. Then, of course, if you find the tangent vector, you can find what is called the unit tangent vector. You just take that divide by the length, you will get the unit vector. That's not important. Now, what is important? Okay, that's another question. It's all calculus, okay, all right. Yeah, so that's exactly what I'm doing. So you see, what you do is that you find this thing called oscillating plane. That contains, that is a plane which touches the curve at the point and contains the tangent to the curve at that point. So it's called the oscillating plane. That comes out of calculus, all right. It is it's all unique. That's why I'm saying this whole thing is, you have to do calculus to prove it, okay. It is unique. It will contain TP and NP. In fact, on the oscillating plane, you will get a special circle. That's called the oscillating circle. That will be the best fitting circle to the curve at that point, okay. And radius of the circle will be the reciprocal of the curvature. or curvature is reciprocal of the radius of the curve. Okay. So, you get the tangent direction, you get this second direction which is the normal, then you have right handed triad given by the binormal. So, this BP is just TP cross NP. Okay. It's like IJK. IJK is I cross J. So, you have TP cap, you have NP cap, the cap means unit vector, then you get TP cap cross NP cap will be cross product of two unit vectors, again give you a unit vector perpendicular to both of them, so that they form a right handed triad. So, this BP, so in fact if I write it like this, is BP cap actually, alright, and this fellow is actually pointing outside the oscillating plane. So, if you want to know what is the motion that is pushing the curve outside its plane at every point instantaneously, it is actually you have to look at the acceleration of this vector, it's called the binormal, and that is what gives you the torsion. That is the thing that pushes the curve out. Okay, all right, yeah. So, let me at least say what I started with. So, otherwise you see the title of my lecture was Rainbows and Gears, and I have not gotten even to bit of the rainbow. So, okay. So, let me tell you something. So, let me give a very short thing, and then again I think I will have to see whether I can get another slot sometime and come back to you and tell you the rest of the story. So, you see, so what's happening? So, you see, give me a curve gamma. What you do is that at every point P, I have the tangent at P, okay. Then I draw there is a normal direction, at P, and there is a center of curvature, okay. Now comes a very interesting thing. If you take, as you change the point P, the centers of curvature will trace another curve, okay. This centers of curvature, that will trace a locus. So, you look at the locus of this OP, this is the locus of center of curvatures. This is what is called as evolute of the curve. Okay. And what actually happens is that this evolute of, so this is what is called evolute of a curve, and what geometry tells us is that this evolute of the curve is actually the envelope of the normals. So, basically what you must understand is that I told you how you get how do you get the center of curvature. You take nearby normals, and where they kind of limit is the center of curvature. So, from that you can see that the envelope of the normals, okay, the envelope of a family of curves is a new curve which touches the original curves, each of the original curves. Okay. So, the moral of the story is that you have the envelope of normals, and what is the beauty of this? The beauty of this is the following. So, let me tell you a few things connected. At least let me get to the rainbow. If I can't get to the gear, at least. Okay. So, you see, you have all seen this. If you have a cup of tea, okay, then you get this shape here, okay, formed on a cup of tea, okay. And if you in school physics, if you give me a convex lens or concave mirror or convex mirror, whatever it is, okay, then you use this 1 by f is equal to 1 by u plus 1 by v, right? You use this formula, and what is it called? Lens formula, but you are missing the important thing. That's okay. That's right. More or less the same with the sign convention. Okay, but is this formula correct? It's called thin lens formula. So it's thin. Okay, and what do you do to and this thinness is really actually very thick. This thinness, that it is actually wrong. Okay, this formula is wrong. All right. So, I will tell you why, and that is connected with this fellow here, all right. So, this thin, did anybody try to, see, whenever you see these formulas in school, do you really try to prove them? You should try to prove them, okay. You just use some, use some little bit of trigonometry, you can prove it. Okay, this thin lens formula is actually only an approximation, it's not correct. Okay, you have to use some approximations. Okay, now so what happens? What really happens is that you see this this formula is incorrect, and also these ray diagrams that you draw, the principles that one of the principles that you use to draw the ray diagram is also wrong. And what is that principle, which also uses this thin business? Do you know that? So whenever you draw a ray diagram, let us say concave mirror, what you do, you take an object. Okay, pardon?
We only consider paraxial rays, like very close to the principal axis.
That's right. Yeah, but
These are small, so we can approximate sin theta to theta.
that's right. Yeah. So where is the mistake in the image that you are putting? See, the idea is the following thing: if the spherical mirror has center of, suppose this is the center of the mirror, and this is the pole of the mirror, and this is 2r. I mean, this is f. I mean, this r is 2f, right? This is what you write.
That is approximation.
And then f is somewhere here, and this is 2f, right? Now this writing r as 2f, that's exactly where you have used thin lens formula. R is not 2f. Okay. And what is the net effect of this? As you rightly say, that's called small aperture. Basically, you take a ray like this, you say that after reflection it goes like this. Okay. By this law, if you give me a spherical mirror like this and I draw parallel rays, okay, then after reflection they should all go through a single focus. Okay, but that does not happen. That's the whole point. Okay, and what you really get is this. Okay. If you take parallel rays and you hit it on a spherical mirror, you will get this curve. You want, what is the importance of that curve? So I will tell you what it is. It is also an envelope. So what is happening is, you see, how do you get this point? You are getting this point because you see that if there is a small portion of this curve here, the curved surface, which is taken as almost thin, and for that it looks like that is the focus. If you slightly take another portion nearby, okay, if you take another portion, okay, then you know your focus will kind of change. And what is happening is these points that you are seeing, you can see, why do you see it? It's because all the light rays are condensing at that point. The flux intensity, the intensity is maximum at that point. You know why that's happening? That's because that is exactly the envelope of all the reflected rays. So what is happening is that when you have this circular thing, when you draw rays like this and then you look at the reflected rays, okay, then these reflected rays kind of coalesce. Okay, there are points where they all seem to, nearby rays seem to meet, and if you plot all those points, that means you are taking the envelope, then the envelope gives you exactly this cardioid. Okay, so I think I can just let me just see whether I can just show that to you. Let me not show it here. Okay, you see that the envelope of all the reflected rays, the envelope is the curve that touches all the reflected rays, and that's the curve where all the rays condense, and that is your nice curve that you get. Okay, that's what you're seeing. So the idea of envelope, and how is envelope related to differential geometry? It is, remember, it is the locus of centers of curvature. Basically what you are doing here is that you are breaking that big spherical mirror into small mirrors of small aperture, finding their focal points and simply plotting them. If you do it in the limit, you will get infinitely many points, and what you are going to get is this curve. So these kind of curves are called caustics. Okay, caustic is you send rays from a point or in a particular direction onto a surface or a curve and look at the reflected rays and form the envelope of all those rays. Okay, and now at least I can justify one word in my title, which is a rainbow. Rainbow is a caustic. Okay, a rainbow is a caustic. Okay, what is happening is that in the sky there are water droplets. Okay, and the different colors are being differentially at different angles because of refraction, they are being reflected. What is happening is that when you see a red colored curve in the rainbow, what you are seeing is actually a caustic surface. What is happening is along that surface in your line of sight, all the red rays are condensing. That's why you are able to see it. Okay, That's how the rainbow forms. The rainbow is an example of a caustic. It's the envelope of the red. That's what you're seeing. Okay, so you're actually seeing envelopes. And how do envelopes connect to come in differential geometry? They are actually loci of radius of the centers of curvature. Okay, all right. Now to complete the story, how are gears going to come into the story? It's very simple. It's just the reverse procedure. So let me tell you about that. So what is going to happen is, well, you see, I told you that we can do the following thing. You have a curve. Then what you do is take locus of the centers of curvature, and you get the what is called as the envelope. This is the so-called, what is this? This is called the evolute, and this is actually the envelope of normals. Okay. Now the point is, from the evolute, can you come back to the curve? Okay. Again, the answer is in differential geometry. There is a process. So just like if you want to go from the curve to the evolute, it's just to look at the locus of centers of curvature. From a curve you want to go to another new curve called the involute. It's called involute. Okay, that is the reverse of evolute. And what is this involute? It is like trying to find a curve for which the given curve is the evolute. Okay, it is like I am already giving you the centers of curvature, and from the centers of curvature, locus of centers of curvature, I am asking you find the original curve. That's what the involute is. And you know, it's so easy to find. So the geometry is easy. So what is the geometry? The geometry is very simple. So what you do is you take this curve, okay, you pick some point P naught, and then you end up at, you take some other point Q naught. Now what you do is that you attach a piece of string like this. You know, you attach a piece of string from here to here. Okay. Then what you do is you start pulling the string out. Okay. When you pull the string, so you know, so the string is stuck to the curve. When I pull it, it will trace a path. That's called the evolute. That's called the involute. Okay. And this is the process to reverse the taking the evolute. So what happens is that, see, when I pull this out, I will get a curve like this. What is the property of this curve? If you give me at any point, if you take any point P here, okay, then, or let me call it as P prime, all right, then what happens is that, you know, I have pulled this much of the string, okay, and you see the portion of the string that I have pulled, you see there are two things that are obvious. So in fact my picture is not so good, let me draw it correctly. So let me put something, it's still bad. Okay. So the thing is that this piece of string that is, so there is this piece of the string that is unwound, and this much of the string is still remaining. Okay, and this that is unwound, you can see two things. The first thing is that this is the tangent to at P. Okay, this, see, when I if you take a roll of paper and if you pull the paper out, you are pulling it out in tangential direction. The same thing happens if I fix the roll and try to move the paper. Whenever you unwind or unwrap something, it's always, you know, that thing is always tangential. And since you are maintaining the shortest distance, that is actually the normal. So the truth is that if you take, if this is the original curve gamma, this is the involute of gamma, you get a new curve. For this involute of gamma, this will be the tangent. So this will be the normal, and at this point this will be the tangent to gamma. So this will be tangent to, let me call this involute, let me call this as gamma dash. This is tangent to gamma dash at P, and this will be tangent to this will be just the, you know, tangent to gamma at P. So, okay, so do you understand this picture? When you and you know, I can reverse this process. What I can do is either I can have a piece of string on the curve and pull it out, or I can do the reverse, namely I can stick a piece of string onto the curve. Either way, what I trace is what is called the involute. Okay. Now what is the beauty of the involute? If you look at the look at this picture, what does it tell you? You see, you take this involute, okay. Is it not clear that the tangents to the original curve are normals to the involute? Okay, and is it not clear that the original curve is the envelope of the normals? Therefore, the original curve is the locus of centers of curvature of the involute, right? Do you see that? Let me repeat it. I have the original curve gamma, I am pulling out a string. That gives me a new curve gamma prime, which I am calling as the involute of gamma. What is the property of this gamma prime? You take any p on gamma prime, okay, p prime on gamma prime, then this p prime to this point p, so this is the amount of length that I have pulled out, and that is equal to this length, okay. My picture is not accurate, okay. This distance is equal to this distance, okay. It's yeah, I mean this picture is bad actually, you know.
So, to P and that is equal to?
I am saying that this is L, this is L, and this is also L.
Oh.
Okay, that is the amount by which I have pulled it out, okay. And I'm sorry, the picture is bad, all right. But the point is that this new curve involute, that its tangent is actually its normal is the tangent to the original curve. That's what I want you to understand. See, this is the portion of the string that is that has been pulled out. That is always tangent to the original curve, but it is normal to the new curve that is being traced, because that is the shortest distance I am pulling it out without tearing, without any tension. Therefore, what is the moral of the story? By construction, this gamma is the envelope of all the normals of the new curve gamma prime. But envelope of the normals is this, is the evolute, it is the locus of the centers of curvature. Therefore, the moral of the story is that if you take gamma prime and you take evolute, you will get gamma, and from gamma to gamma prime it is involute. So, the point is that looking at the centers of locus of centers of curvature amounts to taking the evolute. You can reverse it by taking the involute, okay, and the involute is very, very easy, just either you unwind or you wind, okay, it's as simple as that, all right. So, so the second topic the second word in my title was gears. So, what about gears? So, you see, basically what is happening in gears is basically you have the idea of gears is that you want rotational motion to be transmitted, you want it to be magnified or you want it to be reduced, okay, and then you also want the direction of rotational motion to be changed. You want to change the angle, you want to make a rotation like this into a rotation like this, okay. Now, what is the problem? The usual simple idea is that you just put teeth, okay, you put teeth like this and then you put teeth on the smaller one, and then it will just as you move it by mechanically it will move. So, this is the crude way of doing it. But what is the problem? The problem is that when you do this, when these teeth are going to touch, they are not going to touch properly, they are going to crash into one another, and then there is going to be friction, all right. There is going to be friction, and there is going to be energy waste due to friction, there is going to be speed and all these issues. So, what is an ideal gear? An ideal gear system is one in which there is zero friction, minimum friction at least. Of course, you must always remember that when I say zero friction is an ideal thing, friction is a necessary evil, it will always be there, but you can at least make it minimum. When will friction be? So, the question is, how can you design the shape of the gears so that the friction is the minimum? And guess what the answer is? Where the teeth meet, it has to be tangential, that's correct. And how will you achieve that?
By taking the involute.
You have to take the involute, very good, that's all. So, very good. So, all you have to do is you take a circle, okay, then what you do is at this point you take this piece of thread and then unwind it, you will get something like this. Then at this point, so you keep doing this at every point, okay.
So, the small portion you make the thing.
Pardon? Yeah, and then what you do is you do the same thing in the reverse direction. Okay, that's how you make the teeth. Okay, So in fact, if you want, you can do it like this. Okay. If you do it like this, what happens is that you get these teeth, and now the beauty of this is that if you take two such gears by differential geometry, you can see that when it moves, always at the point of contact, the contact will be always normal to the, therefore what happens is the friction is 0. Okay. So involute gears, so the most important gears are called involute gears, and the principle of involute gears is to form the surfaces of the gears as involute curves to a circle. Okay. And there are more complicated involute gears, there are hypocycloidal gears, there are cycloidal gears, there are all kinds of gears, and it's all differential geometry. Okay. That's what ensures that your gears work, flawlessly. Okay. So it's very simple from the viewpoint of differential geometry. You start with a curve, look at the locus of centers of curvature, that's the evolute. Okay. And the evolute is geometrically the envelope of the normals. When you find an envelope of families of curves, for example light rays, it's called a caustic, and rainbow is a caustic. Okay. And on the other hand, there is an opposing thing. Instead of from a curve, you can form the involute. When you form involutes, and it's a reverse of the process of taking evolute. You form the involute and then you take the evolute, you will come back to the same curve. Okay. But the advantage with involutes is that it allows you to make gears. Okay. So the central point is the radius of curvature and center of curvature. Okay. It's differential geometry. Okay. So you can see, I think if you just go down to you can go down to I think I can show. So there are many things I wanted to show you. So you see, these are the caustics you get on as ellipsoid. Okay. So there are some very amazing things. This is, of course, I told you this shape that's formed on a teacup, and then there is this you must go back and look at this. There is a nice there are a lot of nice pictures of caustics. Okay. And this is from Harvard. You do a search, you will get this. All right. And what is more important is I want you to look at, so there is something called math curve. So there is this math curve. Okay. Please look at this website. Okay. And it will tell you, this is the encyclopedia of curves. There is one in English. I think there is somewhere it says it's in French now. Where was the there used to be an English version, I don't know, wait, let me see. Cube surfaces, yeah, anyway, so you just look at math curve, and I am somehow, there used to be somewhere it says anyway, so there are 2D curves. Okay. And there's a whole bunch of curves, and then you can see if you draw anything like this. This is the Limachon of Pascal. It's called Limachon trisectrix, and then this is, you will see all geometry things connected with that, and then as an epitrochoid, and then with a generating circle and all that, how you get that shape by geometry. You have animations. Okay. And this is a huge encyclopedia where all kinds of curves are there. Okay. And then you also have, this is 2D curves, there is also 3D curves. Okay. And for example, I can show you some 3D curve. Sometimes there are pictures, sometimes pictures are not loading, I don't know why. Catalan, this is the helix of Catalan. So there are all kinds of curves. This is a treasure trove of curves that you can look at. Okay. And then I want you to go to Wikipedia itself is a very good source. Okay. You try to understand radius of curvature, center of curvature, circle of curvature. Okay. Try to understand torsion. Okay. Try to understand what is a caustic, what is an involute, what is an evolute. Okay. And then I want you to look at also involute gears. So involute gears are, I think there is a nice video here. Where is it? So you can see. I don't know whether this is the one, I don't know. So this is a very good video. For example, it tells you how you basically draw a you see this circular thing that's coming out is the involute. Okay, then what you do is that you just draw these involutes, okay, and you draw it for two of these guys, all right. This one wheel of a smaller gear, then your wheel of a larger gear, all right. You draw the involutes for the smaller circle, you draw the involutes for the bigger circle, and then what you do is that you for example, look at the beauty, you draw these two involutes, wherever it meets, that will be perpendicular to the the tangent of contact. That's why you don't have any friction, okay, and this is maintained, and then you just do this by cutting the you cut the gear, so these portions of the gear are actually involutes in two directions, okay. You cut it out, and then I think there must be some animation somewhere. I think it's all there's a good animation even in oops. I think there's one in Wikipedia itself. Where is it? Let me put all. So this is the one. Yeah, here is the animation. Okay, the surfaces of the gears are actually involutes, and you can see that blue thing, which is actually always perpendicular to the surface of two surfaces. So there is no friction. Okay. All right. So this is something that you can see. Okay. So I think I hope I have told you enough, and I have also taken more time. So thank you for bearing with me. If anybody has any questions, you are welcome to ask me.
Sir, what happens if you take like the involute of an involute? Do you get back the original curve?
No, involute of an involute, you are going further away, right? See, from involute, if you want the original curve, you have to take evolute. Okay.
You are making all the tangents into normals. So if you make another tangent of that,
no, be careful. I know what you're thinking, but it doesn't work like that. The problem is that there's also this business of it's not just making tangents into normals. If you want to just make tangents into normals, basically what you're trying to get is an orthogonal family. But it's not just that. It's something more complicated. You see, it's not just making tangents into normals. The point is these normals that you get, their envelope you have to take. Then there's one more step. You have to take the envelope of normals. That should get by. It's not just the normals. It's about the envelope of the normals.
So
that should give you back your original curve. Because you see, where the normals coalesce, they are the centers of curvature, and that locus is where the caustic. That's how you get the caustic. Okay, where the rays have. So if you look at there is a very nice web page in Harvard, some project. Okay, so there is this idea of, see, whatever you see as a lens, this lens idea is very, very general. So you can also have a portion of the earth acting as a lens for an earthquake. You can also have gravitational lensing, okay, and you can study the effects of this using differential geometry. Okay, and then the point is that somehow all these things are applicable in widely varying things such as seismology. Gravitational lensing is cosmology. Okay, they are useful in optics, of course. Okay, so the applications are there are a lot of applications. So differential geometry is kind of it's a very interesting thing to learn about. Okay, any other questions? I think I have taken a lot of your time.
Sir,
yes.
Sir, could you explain the idea of torsion again?
So it's a very so think of it like this. Suppose I'm moving on a helix. Now what happens is on the helix there is you can see that there is a moving plane which is called the oscillating plane. It's like you think of something. I'm just having wings and my wings are just flying across. So that's my oscillating plane. But the point is, why am I going up? There's a vertical component of motion. That's if I don't have that vertical component of motion, I'll just be circling in a plane. I'll not go out of that plane. So how do I measure the vertical component? I'll have to measure the tendency of the plane trying to I have to measure the tendency of the plane trying to move out of itself. Okay, it's like rather you should say at every point there is an oscillating plane, but the curve is trying to run out of that. That means I have to I have to see how this plane is changing. But to check how the plane is changing, it's enough to check how the normal is changing, because the way the normal to the plane changes records the way in which the plane changes. And that's why I have to take the normal to the plane, and that's the binormal. The plane already contains the tangent to the curve. It also contains the normal to the curve, which is along the radius of curvature. Then you take the perpendicular to that, and that is by taking just cross product of these two guys. And you record the tendency of the movement of the plane, which is the same as tendency of the normal to change. That's a torsion. If that is 0, it means that the plane's normal is not changing. The plane's normal is not changing, the plane is stationary. Yes, there are a lot of formulas. There are lots of formulas. Just open, for example, Presley. There's a formula for curvature in terms of vector formula. There's a formula for torsion. In fact, you will get formulas like this. For example, you can write, curvature. Curvature is just gamma dot cross gamma double dot norm by norm gamma dot to the cube. Torsion is gamma dot gamma double dot gamma triple dot scalar triple product divided by norm gamma dot cross gamma double dot squared. You can write formulas like this. Okay, this is for a curve given by gamma dot. So these are all vector formulas. So you can compute. That's what differential geometry is all about. Write out all the formulas, then explain how what you do with these formulas. Okay, right? So that's there in Presley's book. You can look at it. It's not difficult.
Sir, and one more thing, sir. When you say the envelope of a curve, envelope of normals, when you say, is it the point where they tend to like condense? Could you define an envelope?
Yeah, envelope is basically a new curve such that at every point it touches the original family of curves. So envelope of normals means that you have a new curve such that at every point the tangent to that curve is one of the original normals whose envelope which you started with. So you take a curve, then you take all its normals. That's a family of normals. Now you take the envelope of that. That is, you find a new curve through which exactly at each point only one of these normals cross, and where it crosses it actually touches. So this new for the envelope, every curve in the original family is actually having the same tangent, okay, as the new one. So if it's an envelope of family of curves, it means that the new curve has each member in the original family as its tangent. And what you have to do is you have to take the original family to be normals of a curve. If you take the original family to be the normals of the curve, then the envelope of the normals turns out to be the same as the evolute, which is the locus of the movement, the locus of the centers of curvature. And that is the reason why if you take a caustic, whatever you see in a caustic is only those points where the light rays are all coalescing, they're condensing there. The intensity is kind of maximum there. That's why you're able to see it. Okay. When you see a rainbow also, you see what you're seeing is that a portion of that caustic surface which is red in color, and then you because of refraction, because of different wavelengths, you see nearby slightly separated, you see another caustic, you are looking tangential to the caustic surface. That's why you are able to see all the light rays condensed there. When you look at a coffee cup, you see that cardioid kind of thing. Why do you see the light there? That's because all the normals from which the light rays are reflecting, they are like coalescing there, they are condensing there. That's why it's bright. That's why it marks out that surface. So that's how caustics are formed. Okay. So this idea of envelope is very, very important, and of course this idea of envelope is something that's very important. For example, differential equations in physics, there are mathematical ways of writing envelopes. Then there's a theory how to get the equations of the envelope and so on. This is, for example, done in a course in differential equations. Okay. So these are all kind of a lot of differential geometry, differential equations, and of course linear algebra, topology, and calculus is of course used. Yeah, yeah, yes.
Sir, sir, instead of representing the curvature of a space curve as two different components like torsion and then curvature, can we represent it as one vector?
See, in principle, what you do is that it is represented by what are called as the Frone-Serre equations. So it is, you must understand that curvature and torsion are, you can define them as vectors if you want, but actually they are only defined as scalars. But they are defined in terms of three vectors, and what are those three vectors? These three musketeers, the tangent, the unit tangent, the unit normal, and the unit binormal. Okay, and then there is a differential equation that all these curves satisfy, which is T dot n dot b dot is equal to a matrix times T n b, where T is a tangent, n is a normal, b is the binormal, b is T cross n. Okay, and there is a differential equation like this. It's called the Frone-Serre equation. F-R-E-N-N-E-T S-E-R-R-E-T. I think it's single N, I think, or double N. And what it says is, this is the rate at which the unit tangent vector, the unit normal vector, and the unit binormal vector, how are they changing with respect to the original tangent, normal, and binormal. Okay, you must understand that T and B are vectors, therefore the derivatives are also vectors, but T and B is also a basis. Okay, therefore every vector can be broken down in three directions. So you take the directions as T and B and break down T dot n dot b dot, and dot means d by dt or d by ds. Here dot is d by ds, dot here is d by ds, where s is arc length. Okay, so T dot is actually d, so for example T dot is just dt by ds. Okay, now you break this down and you get a very beautiful matrix. You know what, it involves curvature and torsion, so you will get kappa minus kappa, tau minus tau, 0 0 0 0 0, you will get this Q symmetric matrix. Okay, so these are called the Frone-Serre equations. Okay. So anybody who does differential geometry of curves, space curves, the first thing you should learn is this: how do you get this? Okay, so if you want a vector representation, this is the best representation. It's a first order ordinary differential equation in three vectors which form a right handed triad, the tangent, the normal, and the binormal. So this is how you should write it, and you must understand that curvature and torsion by themselves are only treated as scalars, but they are functions, scalar functions. Okay.
Also, sir, how do we know that the yes, sir. How do we know that the oscillating plane is unique? Why is it unique?
That's a good question. So even you can ask the same thing even for a plane curve. Why is the center of curvature unique? Why is the circle of curvature unique? So this is something that will be answered only by calculus. So you have to do it. You see, it's like when a limit exists, it is unique. How do you prove it? So you have to first show. Nobody ever tries to prove uniqueness of a limit. Okay, you only try to guess a limit and then find a way of proving it. For example, you apply L'Hopital's rule or something like that, right? That's what you do. But the uniqueness of limit always comes from some abstract calculus or some abstract analysis. So the uniqueness comes from some abstraction. Okay. So the uniqueness is kind of built in from the axioms, if you look at it finally. But the point is that you have to really write down the calculus. You have to write down everything. Okay, and then it will be clear that you get you characterize it in so many ways. Then you realize that it's unique because because of the characterization. Thank you for your attention.